Welcome everyone, Professor Rosenthal here. In this segment, I would like to take a little bit of time to discuss the formal definition for the limit of a function, because so far what we have been doing was really doing examples of finding the limit using what is known as the shortcut rules. But in mathematics, it's really everything is laid on a very, very solid, rigorous foundation. So that relies on very meticulously defined concepts, definitions, theorems, and so forth. So I'd like to show you a little bit about the actual rigorous definition of the limit of a function. And this did not evolve quickly. It actually came after calculus was already being used. So I'd like to take a few moments to give you the historical perspective about the formal definition, and then we're going to also take a look at one full example using that definition. We're going to learn about the cast of characters. Now, we've already been introduced to Newton and Leibniz, who really laid a foundation of calculus. Late 1600s, it's said that Newton came first and Leibniz soon afterwards, within maybe 10 years difference. And he also added some very important things. So it's not like he copied from Newton, it's like he came up with a different independent way of thinking and also that led to calculus. So there was a problem around 1700s after Newton published his first calculus book and Leibniz came up with his ideas that mathematical community was under attack. And of all the people, there were some mathematicians attacked calculus and also some religious people. So for example, there was somebody with the name of Bishop Berkeley, which we'll get to it, but take a look at how weak some of Newton's definitions were. Like for example, he said, it is to be understood that the ratio of the quantities, that's what a limit is, not before they vanish, nor after, but that with which they vanish. This appeared in my favorite math history book called Journey Through Genius on page 248. Leibniz had also similarly weak statements. In the words of the author William Dunham, he tried to use, incredible amount of mathematical gibberish to explain what a limit was. So no wonder then the criticisms followed. Uh, in his famous essay, The Analyst, a discourse addressed to an infidel mathematician around 1734, Bishop Berkeley wrote, those vanishing quantities, they are neither finite nor infinitely small, nor yet nothing. May we not call them ghosts of departed quantities? So you see, calculus was just, they were making fun of it. As a matter of fact, Berkeley did not um, dispute the conclusions that were being obtained, but he thought that the methods, how they were obtained, were not sound. And how could we ask him to assume these things when other people are questioning the existence of God? So he was saying that, the foundations of calculus was no stronger than foundations of religion. You expect people to believe it on just using faith and not necessarily any kind of proofs. He even went on to say, whether there can be signs of the conclusion. He had these curious, this was one of the many, many curious he had, where there is not evidence of the principles, and whether a man can have evidence of the principles without understanding them, and therefore whether the mathematicians of the present age act like men of science in taking so much more pains to apply their principles than to understand them. So he wrote a very long book on the criticisms. And let me show you. This was like, you can actually find it online, and you can see how long it goes. And every one of these links will take you to curious. He first explains it, and so you see the attacks he's having. Every one of these questions, he's questioning how did Newton come up with his conclusion. So you understand, you get the idea. Calculus is under attack. So what to do? Now, first mathematician who came up with a better explanation was Cauchy, Augustin Louis Cauchy, and I believe he was of French descent. And he came up with one of the better explanations, better definitions, but look at the date, 1821. So many years after calculus was published, and it was being utilized already in examples, applications. But this is what Cauchy said: when the value is successively attributed to a particular variable, approach indefinitely a fixed value so as to end by differing from it by as little as one wishes. This latter is called the limit of all the others. So because it's so hard to explain a movement in mathematical notation and symbols, because as you're approaching the limit L, there is some kind of movement and we're trying to get as close to it as possible. So his way of explaining this was, so as long he uses words differing from it by as little as one wishes. So this is how he explained movement in mathematics. We're approaching towards the limit L. So this is what much better than the ghost of departed quantities like Newton had in his explanations, but still a lot of words, not enough precise mathematical symbols and definitions. Later, Bolzano made some um, great explanations. However, Bolzano's results were not widely seen by others. But in 1840, finally, a former math teacher, Weierstrass, he seals the deal, and I'm afraid I misspelled his name. I believe he spells it as A-S-S, Weierstrass. And he seals the deal and comes up with the final definition that even today we use in analysis textbooks. And here are just to show you the pictures of these mathematicians. So Newton and Leibniz, they first came up with the ideas, but calculus was not on a strong foundation. Then comes Cauchy. He lays the foundation of rigorous calculus, but still he's using a lot of words, not quite enough definitions and symbols. Bolzano comes with the idea, but his work was kind of lost, didn't make the mainstream. And finally, Weierstrass comes up with a definition that we use even today. And what is that final definition, the rigorous definition that put everyone to rest? Um, and that definition is the following. So to say that the limit of a function f of x as x goes to c is L is to say that for every epsilon greater than 0, so no matter how small epsilon is, you can find a small constant delta such that whenever a value x is within delta neighborhood of c, this implies that f of x, the mapped values for those x values, will be within an epsilon neighborhood of L. So this is a very, very complicated definition. It may not make sense to the uninitiated people who have never seen this before. If you're a math major, you're going to see this again. And you're going to probably spend hours contemplating, trying to understand, and don't feel bad about that. I know I went through that stage when I was a math major years and years ago. But the thing is, this definition took more than 150 years to evolve, so don't expect to understand this in one sitting. And here is a picture trying to explain that definition. So I read this somewhere. They said, think of your enemy will come up with epsilon. So no matter how small they come up with the value of epsilon, so no matter how small the epsilon neighborhood is of L, we are supposed to be able to find a delta neighborhood of C so that the values within that delta neighborhood, so everything in this, so that if this is C, so they will tell us what epsilon is. So now we have the epsilon neighborhood of L, epsilon L minus epsilon, L plus epsilon. And so we are supposed to come up with delta corresponding to that epsilon so that whenever any x values within delta neighborhood of C, so say this is delta, so you go C minus delta brings you here, C plus delta brings you here. These are all the x values in the delta neighborhood of C. So everything in that neighborhood, when you plug into the function, look at what the corresponding y values are going to be. They're going to be mapped into this epsilon neighborhood of L. So the catch there is no matter what epsilon is. So if epsilon is this tiny, we should be able to find a corresponding delta neighborhood so that every value of x in that delta neighborhood of C will be mapped into that epsilon neighborhood of L. If you can do this, for every epsilon, you can find a corresponding delta so that the delta neighborhood of C is mapped into the epsilon neighborhood of L, then you have proven that the limit of f of x as x goes to c is L. So again, very complicated looking definition. Let's take a look at one example, see if we can clarify it a little bit better. So we're going to show by using the formal definition of a limit that limit as x goes to 2 of the function 3x minus 2 is equal to 4. So normally, we would do this in 3 seconds, right? If you're just using the shortcut methods, we notice this is a continuous function. We plug the 2 in and we get number 4. But that is not the formal definition, and that will not work in the more trickier cases. And so notice here, this is your f of x, and this is your L, and this is your C. So we're going to try to show that limit as x goes to c of f of x is equal to L. So remember the definition. For every epsilon greater than 0, we need to show there is a delta greater than 0 such that whenever x minus c is less than delta, this means whenever x is in the delta neighborhood of c, that implies that f of x minus L is less than epsilon, meaning that the map values of x's under f, they're going to lie in the epsilon neighborhood of L. All right, so now here is, in mathematics, everything has a symbol. Here's how you would actually write that in a further symbol notation for every epsilon greater than 0. So this upside down A represents for every. So for every epsilon greater than 0, we're going to show that there exists delta. So sideways capital E means there exists. There exists a constant delta greater than 0 such that, so this sideways E almost represents such that, so far what we have said is for every epsilon greater than 0, we're going to show that there exists a delta such that whenever x minus 2 is less than delta, this implies f of x minus L is less than epsilon. And the way you go about proving these things is you always begin with the end in mind. So in a sense, you look at the result, what we're trying to prove, and from there you go back and you try to figure out what delta should be. So you begin with the right-hand side. Okay, so bear with me here. What is f of x minus L for this question? So you would do 3x minus 2 minus 4 under absolute value signs. And so if you put that, simplify, you get 3x minus 6. And from there, go and factor out a 3. 3 is a positive value. It can be taken outside as absolute value of 3, which is going to be 3. And so now you have 3 times absolute value of x minus 2. Now remember, ultimately we're trying to show that 3 times absolute value x minus 2 is less than epsilon, that there is a delta greater than 0 that will imply this quantity is less than epsilon. So we're trying to make that to be less than epsilon. And what that really means is you can divide both sides by 3. That means absolute value of x minus 2 is less than epsilon over 3. Okay, so we started with the end in mind. We kind of tweaked with this last statement, and when we simplified that last statement, that actually gave us this, that absolute value of x minus 2 is less than epsilon over 3. Because we were trying to find a delta that's going to make sure that whenever this inequality holds true, that this inequality holds true. But when we simplify the latter inequality, we got absolute value of x minus 2 is less than epsilon over 3. So do you have any guesses as to what we should choose for delta? So look over here and look over here. So if we choose delta to be epsilon over 3, then it looks like the first inequality will truly imply the second inequality. So again, it's like going backwards. We look at what we needed, and based on that, we decided what delta should be. So choose delta to be epsilon over 3. In that situation, absolute value x minus 2 less than epsilon over 3 implies, now we're trying to show f of x minus L is less than epsilon, but remember f of x minus L in simplified form was this. And since this is less than epsilon over 3, substitute that in. 3 times epsilon over 3, cancel the 3's, that'll be less than epsilon. So we have shown that whenever, for every epsilon greater than 0, we can find a delta, and delta will always be, whatever epsilon is, it'll be 1/3 of that. And as long as you choose delta to be that, x minus 2 in absolute value less than that quantity will always imply that f of x minus L is less than epsilon. So maybe very complicated looking. Again, understand, appreciate, don't worry as to, you're not going to have to do this in my class. I'm not going to have you do it. In other classes, you might be required to do this. Math majors, for sure, you're going to see this again. So hopefully you'll go back and take your time with this and do more examples about it. So I hope I have given you some historical perspective and at least one example to show you how one can go about proving a limit question using epsilon delta proofs.